Hi, everybody. Welcome to Math 60. This video lecture is section 5.4, which is the Cartesian plane, or also known as the Cartesian grid, also known as a Cartesian coordinate system. Cartesian refers to the mathematician, philosopher Rene Descartes, who said, hey, if I have two pieces of numerical information, I could use a two-dimensional way to organize that information. So organizing two pieces of numerical information in two dimensions. So let one piece of information be represented by the variable x, and the other by the variable y. If we do that, then we can visualize that information on a grid where the x values are the horizontal coordinates, or the east-west, and the y values are the vertical coordinates, or the north-south. So like a lot of the math that you've been doing this kind of math in certain ways for a long time. Maybe this is the first time you've seen it this way, but when we need to navigate from one point to another, and let's say we start here and we need to get there, we might take 3 steps east and 2 steps north, or 3 blocks east and 2 blocks north. Right, so most of us have been using this type of thinking for a while, but now we're going to put it in the mathematical context. So this is called the XY plane, or the Cartesian plane, Cartesian grid, etc. And it's a good idea to label your axes, X and Y, so you can keep track of which direction is your X direction, which direction is your Y direction. And it's a good idea to give yourself a step size. Since I have this grid paper, it's pretty easy for me to do this step size like so. And if you think back to when we were just looking at numbers and we just had a number line, the X is a number line, right? And so we go from 0 up, and we also go 0 down. And then the Y is like a number line just turned vertically. So we also count from 0 up. In this case, up is positive and down is negative. And once we do this, it allows us to label any point in this two-dimensional plane, because this point, for example, is 3 steps along the X, 1, 2, 3, and then 2 steps along the Y, 1, 2. And if I take 3 steps along the X and 2 steps along the Y, I'll end up right at that point. And we indicate this information a little more briefly by saying x comma y equals 3 comma 2. And that tells us that we took 3 steps along the x and 2 steps along the y. Here's another point in my plane. By convention, we always list the x direction first and then the y direction. So I like to be really explicit by writing the x comma y equals. Often you just see the numbers, the coordinate point, but I think it's a good idea to write the x comma y. And so we have 1, 2, 3, 4, 5 steps in the x direction, and then 1, 2, 3, 4, 4 steps down, which is negative 4 steps in the y direction. And if I asked you to plot the point xy equals negative 2 comma 4, we start where the lines cross. We start at home, and we're going to count negative 2 steps in the x direction, so that's 2 steps left. And then 4 steps in the y direction, 1, 2, 3, 4. So that's my point, x comma y equals negative 2 comma 4. All right, let's talk about the different features of the coordinate plane. Key features of the XY plane. I'll draw it again. Label these lines. So this horizontal line, that's called the x-axis. And the key thing about the x-axis is all y values are 0 on the x-axis. Sometimes to indicate my scale, I'm not going to draw a whole bunch of little hash marks because I've got the grid, right? So I don't need them. I just indicate my scale. Notice no matter what point I pick on my x-axis, 1, 2, 3, 4, here xy is negative 4 and the y is 0 because I haven't taken any steps. And over here on the right side, 1, 2, 3, 4, 5, 6, xy equals 6 and still 0. So all y values are 0 when you're on the x-axis. It's a little bit of a change, right? X-axis means y is 0. The vertical line is the y-axis, and x values are always 0 on the y-axis. So that point right there, xy is 0 comma 5. The x value is 0 because I haven't taken any steps in the x direction. And this point down here, xy is 0, negative 2, because again, I haven't taken any steps in the x direction. The point where they cross, both x and y are 0, so that point is 0, 0. It's called the origin. And the reason that makes sense is if we look back to how we mapped out our points originally, we always started at the origin, right? You start at the origin and then you go on your trip. So the XY plane has an x-axis where y values are always 0. It has a y-axis where the x values are always 0. And it has the origin where both the x and the y are 0. And then in between those lines, you have what are called quadrants. So I got to draw some more information about the XY plane. X, Y, put my scale on there. So the upper right is called quadrant 1, or maybe with the Roman numeral quadrant I. X and Y are both positive here. All right, that first point we plotted right there, XY is 3, 2. Both the X and the Y are positive. And then we go around and find the other quadrants. Quadrant comes from the square idea, right? So if we think of the square in the upper right as quadrant 1, over here we have quadrant 2, which might be written with the Roman numeral II. Yeah, at least in your homework it is. Which doesn't really make sense because well, I guess Renee would have used Latin and Roman numerals. Here the X is negative and the Y is positive. So that point right there is 2 steps in the X and in the Y, but the X is going to be a -2, the Y is going to be a +2. In quadrant 3, which is the lower left, and in Roman numerals, it's III, X and Y are both negative. And in quadrant 4, IV, X is positive, Y is negative. Yeah. So if you think about any point, you could either be on the x-axis or the y-axis or at the origin. And if you're not on one of these axes, then you're in one of these quadrants. So that covers every possible point. We can never draw the whole thing, but it implies that you could go as big in X as you wanted and as big in Y as you wanted, positive or negative. So this picture covers infinitely small to infinitely large values of both X and Y, or infinitely negative, infinitely positive. So now let's plot some points involving a relationship between X and Y. So far, I just gave you the X and the Y coordinates, and now we're going to have a relationship. We're going to say that Y equals 2 plus X. Or maybe I'd rather write it Y equals X plus 2. And if you think back to last week, we started with the table representation, which I think is great. So I'll scratch out the 2 plus X. It's the same thing, but I'm going to focus on the Y equals X plus 2. And a good number to start with is X equals 0. And if X equals 0, Y equals 0 plus 2. So Y equals 2. Another good number to try is X equals 1. And so Y equals 1 plus 2 or 3. And maybe another number if X equals 2, Y equals 2 plus 2, which is 4. It's not a bad idea to put some negative values in for X. They don't have to go sequentially, so I could stick a -1 in there. -1 plus 2 is +1. And so if I want to plot these points, X, Y, and put my scale on there, my information tells me when X is 0, Y is 2. So I start at the origin, and I don't take any steps in the X direction, and then I take 2 steps in the Y direction. So that's 0, 2. And then when X equals 1, Y equals 3. So I take 1 step in the X and 3 steps in the Y. When X equals 2, Y equals 4. And if X equals -1, so I take 1 step to the left with X and then 1 step up with Y, and I get 1, -1. And notice that these points are in a line. I could connect them with the single line that's going to go through all of these points. And that means that the relationship, if the coordinate points generated by a relationship between X and Y are all on a line, then the relationship is called linear. We say we have a linear relationship between X and Y. And a lot of math ends up being something linear or close to linear. So let's look at an example, another example. Let's look at the relationship between X and Y. It's going to be 2X plus 5Y equals 10. And let's see if we can plot some points. And so the way we might start is we might do an XY. Notice I have to do some work. To figure out Y each time. It's not quite as simple as the previous example where I had that my Y value equals something with an x. Now I have y and x on the same side, but I can still do some work. If I let x equal 0, then I'm saying 2 times 0 plus 5y equals 10, which means 5y equals 10, which means y equals 2. I kind of ran out of space there. When x is 0, y is 2. Let's try x equal to 1. And 2 times 1 plus 5y equals 10. So I have to solve this for y. And I'm going to end up getting 5y equals 8 or y equals 8 over 5, which is 1.6. Yeah. And if x is 2, I'll let you confirm the arithmetic. Six. Yep. Let's see. That's going to be well, I better do it because my brain is slow today. Aha. I was making mistakes in my brain, but once I wrote it down, it made sense. I'm going to get y equals, let's see, 10 minus 4, so 6 over 5, which is 1.2. Keep going. Let me jump up and just, let's say y equals 5, or x equals 5. So then 2 times 5 plus 5y equals 10. That means that 5y equals 10 minus 10, which is 0. So y actually equals 0. So now I have a couple points and I can plot some of these points. When x is 0, y is 2. When x is 1, y is 1.6, which is a little more than 1.5. So I can stick that in there. That's why I'm on a grid, so I can get close. When x is 2, y is 1.2, so it's going to be like there. And when x is 5, 1, 2, 3, 4, 5, y is going to be 0. So now I come out here a little bit farther, but I can see these points still all fall on a line. So I still have a linear relationship between x and y. Okay. Let's see. One last example. What if we have a picture first? Let's look at an example here where I have minus 2x plus y equals 1. And then I give you a couple points and I ask which points satisfy this equation. Okay, so which of these points match the relationship or the equation? And this is also something you did last week. Only last week I gave you coordinate pairs, and now I'm giving you points on the graph. So we can still do the same process, but now the first thing we should do is identify what the coordinate pairs are. So the first one up here, x is 2, and y is 1, 2, 3, 4, 5. So 2 comma 5. The second point over here on the right, x is 5 and y is 0. I'm on the x-axis, so the y coordinate has to be 0. And then this point down here to the left, x, y equals, looks like it's -2 comma -3. And once I have those coordinate points, then I just test them in my relationship. Let's test x, y equals 2, 5. So I have -2 times 2 plus 5, which is -4 plus 5, which is 1. So that one works. Let's test the other one, or the next one, the 5, 0. So I have -2 times 5 plus 0. Oh, that's -10. Doesn't equal 1, so that doesn't work. And if we test the last one, xy equals -2 comma -3. I have -2 times -2 plus -3, which is 4 minus 3, which is 1. Yep, that does work. So the points that match the equation are the first one, 2 comma 5, and the third one, -2 comma -3. And that actually means that any point on the line connecting those two dots would satisfy the equation because it's a linear relationship. And notice how if the line connects these 2 points, it definitely cannot reach out and touch the 5 comma 0 point. That would not be a nice straight line. All right. That covers 5.3. The basic ideas of what are the pieces of a coordinate plane, right? The axes, the quadrants, the origin. How do you label points? And then how do you check if points on your XY plane satisfy some kind of relationship between X and Y? Might be a short week. I think Wednesday's probably going to be a catch-up day for us, which is fine with me. So we're just going to cruise right along and start section 5.5 and see how far we get. Section 5.5 is graphs of linear equations. So we already know that linear equations make lines when they are graphed. Linear equations can, sorry, well, those graphs can be, I should use a different color. I'm gonna start over. All right. Section 5.5. Graphs of linear equations. And the whole reason we call them linear equations is because they make lines when you graph them. Now, to say something makes a line doesn't tell you what direction it's going. You could be going up and to the right. You could be going I'm not putting units on here because that's not the focus, just for seeing what those pictures look like. But you could always add units. They could go down and to the right. A linear equation could give you a completely vertical line straight up and down. Or it could give you a completely horizontal line. Totally flat. These are basically the four possibilities. You can go up and to the right, down and to the right, totally vertical, or totally flat. Anything that doesn't look like this is not linear. So some examples of non-linear. Pretty much if it curves. So it could look like this. As soon as you get into non-linear, there's all sorts of different possibilities. It could look like this. Right. So when you're looking at a graph and you want to know if it's linear, just is it a straight line or not? As soon as you know a graph is linear, a graph will be linear if and only if the equations, the equation of the graph, of the relationship, has only x's and y's with no powers. For example, Linear might be something like y equals x plus 2. And there's no power on the y, there's no power on the x. Another linear one might be 2x plus 5y equals 10. No power on the y, no power on the x. You don't have to have both x's and y's, actually. I could have x equals 2. Right? No power on the x. Since there isn't a y, then there's definitely no power on the non-existent y. So it still fits that rule. I could have it be linear where there's no power on the y. And since there is no x, there's no power on the x either. I can make it look super complicated. -2 times x plus y minus 3 times x minus 4 plus 7y equals 22x plus 18y minus 5. Super complicated. Nothing I'd really want to work with. Still linear because the x's and the y's have no powers. And using the tools that you developed, we could actually simplify this down until there's a single x and a single y. And it would look something like one of these simpler versions. If there are fractions, the x and possibly y must be in the numerator of the fraction. So if I have a fraction like x plus 1 over 2 equals y, this is okay. That's linear. But it's not linear if one of your letters is in the denominator. You can't have powers of x or y bigger than 1, which is kind of the same thing as saying there isn't a power. So a nonlinear function might look like x squared equals y. As soon as you have a power on the x, it's not going to be linear. I'm being a little yeah. I guess I'd have to say unless they all have the same power. But I'm not going to focus on that. We're just going to talk about if you don't have powers that are all 1, then it's not going to be linear. Another nonlinear might be y plus 1 and then you square it equals x. All right, I still have a power that's not equal to 1. That's going to end up on the y, so it's not going to be linear. If ever you wonder, am I looking at something that's linear or not? you can use a graphing calculator. I recommend Desmos. The first one I wrote down was y equals x plus 2. Yep, that's a straight line. And the next one I wrote down was 2x plus 5y equals 10. Yep, that's a straight line. And then I wrote x equals 2. That's the vertical line. Notice no matter where I am on this point, the x coordinate is 2. That's what it means to say x equals 2. It says I don't care what the y value is, the x value is 2. Straight line. And then I did y equals 3. And again, that's a straight line. It doesn't matter what x value I pick, the y always equals 3. And then I did the -2 times x plus y minus 3 times x minus 4. At a certain point, I might have an issue here if it's too much for Desmos to graph, but let's just see if this is going to work. Yeah, right? Straight line. Nothing I'd necessarily want to work with, but certainly all these points fall on a nice straight line. And then I did x plus 1 over 2 equals y. That's a straight line. But when I switched it and I did 2 over x plus 1 equals y, definitely not a straight line. And if I did x squared equals y, also not a straight line. And y plus 1 quantity squared equals x, also not a straight line. What's the button you use?
Or like when you're writing it.
Oh, when you're doing it by hand? Yeah, so you get some points and then you connect the dots. Yeah. I don't think we'll be doing that in this class in Math 70. No. Yeah. But it's similar to when you graph linear, you get some points, you connect the dots, and in linear, you realize, oh, they all connect in a straight line. If it's something like a squared, you're going to say, eventually you'll notice, oh, they kind of make a U. All right, so you would start with when x is 0, y is 0. And then when x is 1, y is 1. And then when x is 2, y is 4. And when x is 3, y is 9. And then when you connect them, it's going to kind of curve up.
Oh.
And then you also do when x is -1, -1 times -1 is +1. -2 times -2 is +4, and it curves up on the other side. Yeah. All right. Okay, linear, nonlinear. And then we're gonna make some equations. Okay. And that was a good question. We're going to focus on the linear ones, but it's the same process that I'm going to give some examples right now. Graphing. Linear equations. So let's graph by hand that first one, y equals x plus 2. And the way that I recommend doing it is generating a couple coordinate points. Always nice to start with 0. When x is 0, y is 2. X equals 1 is usually a good choice. When x is 1, y is 1 plus 2, so y equals 3. And maybe we'll do another point just for good measure. That will confirm that it's probably linear. If I do x equals 2, y is going to be 4. So with a couple points in hand, oh, and by the way, this brings us back to the idea of symbols, words, numbers, and pictures. Well, graphs are pictures. And what I'm asking you to do is to go from the symbols to the graphs. But there's no reason why you can't first go to numbers and then go to graphs. That's the idea of using the table. So let's generate some numbers and build our graph from the numbers. And that's also your question with a squared is like, oh, how am I supposed to do that? You make a table first, right? Don't try to go directly from symbols to graphs. Go through the numbers first to give you some reference points. So with my scale, when x is 0, y is 2. When x is 1, y is 3. When x is 2, y is 4. I mean, things could get weird in the future, but so far it looks like it's going to be a line. And so I just connect them as best I can. And there's the graph of that equation. We put arrows at the end because the options for x go from all the way from negative infinity to positive infinity. And if I come back to my table, I could put 100,000 in for x, I'd get 100,002 for y. And so if this picture could go to the right for a super, super long way, that line would still continue. And so to show that, we put arrows on the ends of our lines. And sometimes graphing systems don't put the arrows. Like in your homework, I don't think it'll have an arrow on the end of the line. In Desmos, it doesn't put an arrow on the end of the line. There it is. In Desmos, you can zoom out, which is nice. And you can actually zoom out a whole lot. Like, I think it will just keep going.
Yeah.
And going and going. And notice it's still a line. Here I am at, there's the 100,000. And when x is 100,000, y is 100,002. All right, so Desmos is really nice for that sort of thing. Oh, and then if you want to zoom back in really quickly, press the home button and it'll zoom back to.
What is like no has an ending?
Can you say it again?
Pretty much it never has an end.
That's correct. These lines never have an end. I could go up to 1,000,000. I could go up to 1,000,000,000, 1,000,000,000,000, and the mathematical operations would still work. It will work even as x goes out towards positive infinity or as x goes out towards negative infinity. All right, let's see. Let's do another example. Nope, I wanted. Okay. Let's do y equals 4x minus 7. And let's try to graph that one. So before graphing it, I'm going to build a table to get some reference points. And it's always nice to start with x equals 0. When x is 0, you have to be on the y-axis. That's what it means for x to be 0. Right? So it gives me a good starting reference point right in the middle of my picture. When x is 0, y is 4 times 0 minus 7. So y is negative 7. When x is 1, y is 4 times 1 minus 7, which is negative 3. When x is 2, y is 4 times 2 minus 7, which is negative 1. I'll go a little bit farther. When x is 3, y is 4 times, oh, I think I did that wrong, right? 4 times 2 minus 7 is 8 minus 7, which is positive 1. But the nice thing about getting it wrong in the table is if you go to graph it, you might notice that you messed up. 4 times 3 minus 7 is 12 minus 7, which is 5. So now I have some reference points. Got to draw my axes big enough to accommodate my reference points. When x equals 0, y equals -7. 2, 3, 4, 5, 6, 7. So it's starting down here at x, y equals 0 minus 7. Starting is not really the right word because it's going to continue to both sides. And when x increases by 1, y is going to increase up to -3 right there. That's 1 comma -3, and then 2 comma +1 will get me here. And if I had done 2 -1 the way I originally tried to, I would have said, oh gosh, that's not on a line. Right? It goes up and then over. So that might have been a clue. And then when x equals 3, y equals 5. And so I can connect these points, stick an arrow on the end to represent they continue forever. Let's look a little bit more closely at the symbols and the graph, and we're going to be able to recognize some things. First of all, when I have an equation written y equals a number times x minus 7, that constant term right there is exactly the y-intercept. Notice it worked in the previous example too. I had y equals x plus 2. Right there, 0 comma positive 2 is the y-intercept. And then let's look at y equals 4x minus 7. Every time x increased by 1, y increased by 4. Each time x added 1, y added 4. And we can see that in our picture. When x goes over by 1, y goes 1, 2, 3, up by 4. Over by 1, 1, 2, 3, up by 4. Over by 1, 1, 2, 3, up by 4. And that's exactly this number multiplied by the x. The 4x tells you when x goes up by 1, y goes up by 4. So this equation, y equals 4x minus 7, is what's called slope-intercept form. The slope is how y changes as x changes, and the intercept is the y value when x equals 0. Slope-intercept form is the most common way to write a linear equation because it contains a lot of useful information and allows you to graph it really quickly. In a lot of settings, you might think about a starting point, which is starting when x equals 0. So knowing that y-intercept is useful. Let's do one more example. And then we'll be done with lectures for the whole week, actually. Let's also write this in slope-intercept form. Y equals 1/3 x plus 4. So I'll build a table. start at x equals 0. That must mean that y equals 4 because 4 is the y-intercept. Now, if x goes up by 1, that's 1/3 times 1 plus 4. That's 4 plus 1/3, which if I want to get my fractions is 13/3, but this is kind of less important. Same idea when x is 2, that's going to be 4 plus 2/3, which is 14/3. And when x is 3, y is going to be 4 plus 1/3 times 3, which is 4 plus 1, which is 5. And now I feel like I have some information for drawing this graph. Based on where I'm starting, I can draw my x-axis a little lower because it looks like I'm going to be mostly going up. So when x is 0, y is 4. X is 1, it's a little bit bigger than 4. But when I get all the way out to x equals 3, that's when I get out up to 5. So there's this point right there is xy equals 3 comma 5. That's really all I need to draw this straight line. I only need the 2 points. And in this case, notice that it's when x increases by 3 that y increases by 1. So the slope, which is 1/3, tells me that when x increases by 3, y increases by 1. 1/3. So you often see slope written as the change in y divided by the change in x. Y goes up by 1 when x goes up by 3. 1 divided by 3. And another way you often see this written is rise over run. Run is the 3 steps to the right. Rise is the 1 step up. So that's actually a preview, this idea of pulling out the slope and the y-intercept from your formula. The actual work you're doing is just getting to graph it, plotting some points and graphing it. But I wanted to give you a preview that all of these ideas are related. You can figure out, I'm going to use this previous example. You can figure out how y changes as x changes from the formula. Y goes up by 4 when x goes up by 1. You could also figure it out from the table. When x goes up by 1, y goes up by 4. And you can also figure it out from the graph. When x goes up by 1, y goes up by 4. So understanding the change in y as x changes is, first of all, really important. And second of all, something you can get from any of these representations. You can also figure out your starting value. -7 from the formula, 0, -7 from the table, or there I am on my y-axis, and the value is -7. So all 3 of these representations contain all the information about the relationship that you really need. All right, that wraps it up. I will stop the recording now.